Okay, so this is a little explanation of how we get the nth term in a sequence for modelling geometric growth or decay. So we know how to work out, just by using our calculator, repeatedly each term in a sequence, but if we want to know what the 100th term is in a sequence, then it's much faster if we use this method. So for instance, if we use of how to find the rule, we invest $2,000, as an example of how to find the rule, we use a question. If we invest $2,000, sorry, pen's not working properly, so we invest $2,000 at a rate of 5%, and we let Vn be the value after n years. Okay, so Vn is the value after n years. Okay, so if we're writing a recurrence relation for this, this would look like, so our recurrence relation becomes V of 0 equals 2,000, and then each term is equal to Vn plus 1, or each subsequent term is equal to Vn plus 1, which would 1.05, which is our rate, plus 100%, times the current term. Okay? So, as we've learnt before, that we get that point from the fact that R equals 1 plus 5 over 100, which was our rate for geometric growth. Okay, so that's what we know so far. The sequence, if we map that out, this sequence looks a bit like this. We've got V of 0. I'm going to jam this over here because I feel like I'm running out of room. I'm going to cut that off there. Okay, so as a sequence, we have V of 0 is equal to $2,000. Then V of 1 is going to be equal to 1.05, so the rate that it's increasing, times V0. Now, this is where we get the change coming in. V of 2, because we know that each subsequent term is the previous term, as is shown up here, previous term times 1.05. If we look at it in this case here, V of 2 has to be 1.05 multiplied by 1.05 times V0. Okay, because our previous term, our Vn, was 1.05, was this. So that's our previous term, just Vn. So V2 is 1.05 times 1.05 V0. Now that equals if we expand it, 1.05 squared times v0. Next term, v of 3, is going to be equal to 1.05 times 1.05 squared times v of 0. Okay. Remembering that our previous term was 1.05 squared times v0, so that becomes that point there, and so on. So you can see what we're building on here. So each term is equal to the previous term. So we have the previous term, and we multiply that by 1.05 again. So each time we're growing, we're multiplying by 1.05 again. Now if we were to follow this pattern, what it becomes is, and we're starting to create the general rule here, what we get is Vn equals 1.05, so the rate that we're growing at, to the power of n, okay, times v0. And what I should have put in that last line was, so if we expand this out, we get that all equal to 1.05 cubed now times v0. Okay. Now what we want to look at here is the fact that here for v of 2, okay, we ended up having our rate squared. Okay. For v of 3, we ended up having our rate cubed. Okay. So that's why here v of n, whatever n equals, whichever term in the sequence we're looking for, we're going to use that as the power. So 1.05 to the power of whatever n is times v of 0. Okay. So to generalise this now, what we've come up with is we now know, we now have a recurrence relation. So a rule might help if I don't draw in a highlighter. We've got a recurrence relation. Okay. Okay, something just went very odd with the slide presentation then, so hopefully we're all back on track now. So the recurrence relation, so what we've learnt now is from the previous chapter, and I know exactly what's happening now. Every time I touch the screen in the wrong spot, it is taking me to the wrong slide. Okay, let's try again. Recurrence relation. So I want to do this. So my recurrence relation for this last problem that we, sorry, not for the last problem. So our recurrence relation, the general rule is v of 0 equals our starting value and v of n plus 1, being our rule, is equal to r times v of n, so our rate of change, times the previous value. Then what we've just worked out through that recurrence relation is how to find the nth term. So the nth term in a sequence is equal to v of n, so whatever term we're after, the rate that it changes to the power of n multiplied by v of 0. Okay. Now, the last example was for compound interest. Now if we want to do it for a reducing balance depreciation, so for a reducing balance, probably shouldn't write in cursive because it doesn't come up too well on the screen. So reducing balance depreciation, the only change that we get is the same as when we were doing the recurrence relation. If it was growth, then our number would be greater than 1. If it was decay, our R value would be less than 1, and the same for the reducing balance depreciation. So for example, our R value would equal 1 take away R over 100. Okay, so for instance, that last problem, if we were reducing the balance by 5% geometrically, we would have 1 take 5 over 100, and that all equals to an R value of 0.95. So I hope that helps out with the finding the nth term for for geometric growth or decay.